Hello everyone, my name is Manoj Chandra Haldar. I am a third semester student pursuing my Master of Applied Science in Energy Systems Engineering at the Memorial University of Newfoundland, Canada. Today I'll present to you the techno-economic optimization of a zero-emission energy system for a Canadian remote community as part of my course project work, Instrumentation and Control of Energy Systems. So let's begin without further ado. We all know that Canada is a well-developed nation with a GDP of $1.6 trillion per year. Despite being a well-developed nation, there are over 280 communities in Canada with approximately 200,000 people who are disconnected from the North American electrical grid and natural gas distribution systems. Most of these indigenous communities are situated in the northern parts of Canada in the states of Nunavut, Yukon, and Northwest Territories. Talking about Nunavut alone, 55 million liters of diesel is being purchased every year to empower these remote communities. As a result, 733 tons of carbon dioxide emission was caused in 2019 alone, which clearly indicates that these remote communities are entirely dependent on fossil fuel for their primary source of heat and power. Additionally, the carbon dioxide emission has increased by 26% since 2005. For my research project, I have selected a site called Pangiritang, which is situated in the province of Nunavut on Baffin Island. On April 2nd of 2015, a massive fire at the 40-year-old diesel generator power plant infrastructure in Pangiritang, Nunavut, caused a month-long state of emergency in the community of 1,600 people. As you can see from this picture here, it is the actual picture from that incident. Therefore, it is of prominent importance to develop zero emission energy source using renewable sources like solar, wind, and hydro to empower these communities in Canada. So without further ado, let's have a look at my research project. Referring to the novelty of this project, we all know that Pangitan is situated in the Baffin Island in the state of Nunavut, which is very close to the North Pole. So this area faces severe weather in winter and low sunlight hours during that time. Also, the previous research study which were developed to implement the renewable energy resources for the remote communities in Canada were somewhat connected to the electrical grid itself. However, Pangitan is entirely disconnected from the electrical grid, and previously no research study has been done for any northern indigenous community of the state of Nunavut, Canada. Therefore, disconnected from the electrical grid makes this site unique for my research project, which we will have a detailed look. Now, I want to present to you the methodology I have used for my research study. First of all, I have conducted the community load assessment for the community of Pangitang Nunavut. After that, I have conducted a resource assessment to implement renewable energy integration. Renewable energy resources like solar, wind, and tidal energy was used to develop the zero-emission hybrid energy system for this research. After that, I have made a system architecture using the Homer software tool. Then I have selected the system components like PV module, wind turbine, inverter, and battery system to conduct the simulation in Homer software. After that, I have conducted an economic analysis for the electrical components that I have selected to generate the simulation in the software. Finally, I have generated the simulation using Homer software and came up with various renewable energy solutions for the remote community of Pangitan. After that, I have discussed the results and outcomes of this research study from the Homer software, which we will have a detailed look right now. Now referring to the community load assessment, Pangitan has 1,480 residents in total, and this community has a peak load demand of 1,208 kilowatt in winter. Currently, this community is powered by two number of 1,100 kilowatt diesel generator and one 680 kilowatt of diesel engine. which entirely indicates that this community is highly dependent on fossil fuel power generation. Referring to the seasonal profile, we can see that January month has the highest load demand, which is about 1200 kilowatts, and this load demand slowly decreases as the summer months progress. We can see that the month of August has the lowest load demand, about 700 kilowatts, and after August, the load demand slightly increases till January, which has the highest load demand. Referring to the resource assessment, Pyeongtaek receives excellent solar irradiation during summer months from June to September and the least during the winter months from January to April. Throughout the year, the hourly average solar irradiation ranges from 0 to 0.8 kilowatt per meter square. From the average daily incident solar energy in Pyeongtaek graph, we can see that it can generate the highest power generation from PV modules in June, which is about 6 kilowatts, and in the winter months in January and December, it doesn't any solar energy output because it doesn't receive any sunlight during harsh winter months. Now, referring to the wind resource, this area offers tremendous wind energy potential, which can generate a large number of electricity with efficient wind turbines. The windiest part of the year lasts for 3.5 months, ranging from September to December, with an average wind speed of approximately 12 kilometers per hour. From the average wind speed graph in Panjitang, we can see that November and December month has the highest wind speed of about 13.7 kilometer per hour, and July has the minimum wind speed of about 10 kilometers per hour. However, in July, Pyeongtaek receives the high solar energy output, so the minimum average wind speed can be replaced by solar energy in the summer months. As we all know that a wind turbine requires a wind speed of 12 to 18 kilometer per hour to generate the highest wind energy. Pyeongtaek is highly favorable for wind power generation throughout the year. Now referring to the tidal resource assessment, this community is located on the bank of Labrador Sea at the northernmost point of Cumberland Sound, 50 kilometers to the south of the Arctic Circle on the wide expanse of an old beach. Annually, the water level ranges from 3.8 to 4 kilometers on average. Also, during a low tide, the water level is 1.5 meters on average, and during high tide, the water level is approximately 6.3 meters high. Referring to the monthly average water level, we can see that the highest water level is more than 4 meters in January, which decreases as summer progresses. The lowest water level is in the month of May, with about 3.8 meters. After the month of June, the water level slightly rises to approximate 4 meters in December. Therefore, the water level is on average from 3.8 to 4 meters during each month. The tidal resource is suitable for tidal power generation. For this study, we have considered a 100 kilowatt tidal plant to generate renewable energy from the seashore. Now referring to the system architecture of the hybrid energy system, it consists of an AC and a DC bus. The AC bus is directly connected to the wind turbine, hydro energy inverter, and the electric load, whereas the DC bus is connected with the battery system and the PV module. Now, this zero emission system considers Canadian Solar Max with a model number of CH6U340M PV module. The solar system has a flat plate with an efficiency of 17.30%. Referring to the wind turbine, the system consists of a 1.5 megawatt wind turbine, a General Electric brand. It has three-blade upwind horizontal axis and is constructed to operate in upwind configuration at 10 to 20 revolutions per minute. The system also consists of a hydroelectric power source. A miniature hydrokinetic turbine is taken into consideration for this study. The system also consists of a battery system. The proposed research study has a 4-hour 1 megawatt battery storage system because of the harsh weather conditions in the north and intermittent renewable energy sources. Additionally, the system also consists of an inverter which has a capacity of 250 kilowatt with a 95% efficiency rating. Now, the economic analysis is carried out mainly based on the cost of energy and net present cost calculations. First equation is used to calculate the cost of energy, where C of A is the total annual cost. Secondly, the cost of net present cost is done using equation 2, which is the capital recovery factor achieved from equation 3, and the discount rate is also measured from equation 4. The project lifetime in this study is considered 25 years with an annual inflation rate and a nominal discount rate of 2% and 8% respectively. Now we shall have a look at the simulation and the final results. After providing all the data in Homer software that we have discussed previously, including the solar, wind, and tidal resource assessment, community load assessment on a monthly basis, and the economic equations discussed previously, the Homer software ran about 6,618 simulations in total. Among all the simulations, 3,802 were feasible and the rest were infeasible due to the capacity shortage constraint. Finally, the software has provided us with three different scenarios which can meet the net zero hybrid energy solution for the community. As you can see from the table, the first solution would be PV, wind and hydro. The second would be wind and hydro, and the third solution can be PV and hydro. From the table, we can also see the cost of energy, net present cost, and the capacity of the energy sources, including the excess energy, unmet load, and the capacity shortage. From the table, we can also see that the cost of energy is minimum, which is about 0.5 cents per unit for PV, wind, and hydro solution. For the second probable solution, the cost of energy is 0.69 cents per unit, and for the third probable solution, the cost of energy is $2.43 dollars per unit. The system also gave us an estimated net present cost for the first solution, which is about 19 million and 24 and 86.7 million for the second and third solutions respectively. Now we are going to discuss the simulation results and the probable actions in details. Now from the simulation, Homer has generated three probable simulations which are the final outcomes of this research study. The first probable solution consists of PV, wind, and hydro power source. The optimum system has a capacity of 3,307 kilowatt-hour of photovoltaics, 1,470 kilowatt of wind turbine, and 98 kilowatt of hydro, with an 819 kilowatt of inverter. As you can see from the graph, that most of the energy is generated from the wind turbine itself because of the favorable wind speed throughout the year. The solar output is generated throughout the month starting from February to October because of the favorable solar irradiation during those months. The rectifier power output is also consistent throughout the year. However, the hydropower output is produced in minimum for the system which is about 90 kilowatts starting from the month of March throughout November. The whole system, in the whole system, the lithium-ion battery has the most significant operating cost, which is about 5 million, and this cost makes up the overall operating cost of 19 million, including the wind and hydro, which have the low operating expenses. Therefore, this optimum solution is able to generate the entire power from the Pangitan community throughout the year. Now, the second probable hybrid energy solution consists of wind and hydro resource only. This proposed system has a capacity of 1497 kilowatt of wind turbine, 98.1 kilowatt of hydro, and 1014 kilowatt inverter. From the graph, we can see that 98% of the energy is generated from the wind turbine throughout the year because of favorable wind conditions. However, the small hydroelectric unit only generates up to 90 kilowatts throughout the months starting from April to November because of the tidal conditions in Pangitan. This system has a capital expense of 14 million. The 1 megawatt lithium-ion battery dominates the cost components like the previous power solution, accounting for 52.4% of overall capital expenditures, followed by the wind turbine, which is about 26.78%, and the smallest hydro turbine, which consists of 20% of the overall capital expense. Now referring to the last probable solution, which consists of solar and hydroelectric energy option. This system has a capacity of 16,000 kilowatt photovoltaics and 98 kilowatt of hydro, including a 960 kilowatt inverter. As we can see from the graph here that most of the energy is generated from the solar PV module from the month of February to November, and a minimum amount of hydro energy is generated through the year, which is only about 90 kilowatts. The lithium ion battery bank is charged throughout the year, and it supplies the electric load during the winter months where PV and hydroelectricity produces the minimum output. The third proposed system has a capital expense of 56 million, which is the most costliest proposed system. Likewise, the previous systems, it consists of the battery component, which is the costliest component, accounting for 90% of overall capital expenditures, followed by the solar and hydro, which is about 6% and 4% respectively. Now, what are the final outcomes of this research study? According to the research presented above, the PV wind hydro-based hybrid energy system results in the lowest cost of energy, comprising of about 55 cents per unit of the system configurations examined. Although other configurations with various equipment sizes and costs can meet the load need, just like the second and third probable solution, the first solution consisting PV, wind, and hydro components is the best choice as the NPC of the system is about 6 million, which is about 19.38% lower than the second and third probable solution, and has the minimum capital cost than comparing to the other two systems. This research study also compared with other research study for a community in Manitoba suggested by Batari et al. Which comprised wind diesel solution for off-grid hamlet, and they reported a cost of energy of about 0.49 cents per unit. Therefore, this research study is competitive with other research study and gives a zero emission hybrid energy system for the remote community of Pangitan. To conclude, this study establishes the optimized hybrid energy system with photovoltaics, wind, and hydro resource for supplying power to the indigenous settlement of Pangatang in Canada's Nunavut province. The hybrid energy system with an alternatives of wind, hydro, and battery are comparable in terms of cost of energy and net present cost. The suggested system is economically and technologically feasible, and the cost of energy offers excellent value as compared to the diesel-only alternative. However, due to the financial limitations, installing such a system is far from reality. The project's biggest drawback is the high initial cost. Therefore, the government should take proper initiative to implement the zero emission hybrid system in the northern Canada in the province and therefore reduce carbon dioxide emissions by a significant amount in the future. These are the references I have used for this presentations. I hope you all enjoyed my presentation. If you have any questions, please feel free to contact me in the future. Thank you.